It's a real honor for me to introduce Søren Larsen, who is visiting us from the Radboud Universiteit Nijmegen. Søren is a world-leading expert in anything related to star clusters and star cluster populations. I think originally he was interested both in young cluster populations but also globular cluster populations. Has been making a lot of use of big facilities like the Hubble Space Telescope and Keck. And more lately, Søren has become interested in the problem of multiple populations in globular clusters, and I think that is going to be the main focus of his talk here today. Søren started doing his PhD at the University of Copenhagen in collaboration with Bonn, where he worked with Tom Richtler. After that, he went to Lick Observatory at UC Santa Cruz to do a postdoc, after which he then went back to Europe to ESO, where he became an ESO fellow, and after that ESO staff. Then went to Utrecht University in the Netherlands, where he stayed till 2012, after which he moved to Nijmegen, where he is currently as a lecturer. And yeah, Søren, I very much look forward to your talk, and the floor is yours.
Thank you very much. Yeah, thank you very much for the introduction. So it's a great pleasure to be here in Heidelberg, seeing so many familiar faces that I haven't seen for a while, and also quite a few new ones. So that's great. Today I'm going to talk about globular clusters. As Didrik mentioned, this is something that has kept me busy for quite a few years now. And I'm going to start out with a little bit of a general introduction here, just giving you a general overview of some things that we know about globular clusters, or that we think we know about globular clusters, and then moving on to some of the more specialized stuff. So this doesn't actually seem to be advancing, so maybe I'll just do like this. Okay. All right, so let's just enjoy this nice picture here. This is, of course, a globular cluster, M15. The giveaway is this little planetary nebula up there, right? So there's about 150 globular clusters like this known in the Milky Way today. M15 was discovered 250 years ago or so by Maraldi, and it was included, of course, in Messier's catalog that contains about 30 globular clusters. But the first to really study these objects in some detail, resolve them into individual stars, was William Herschel, right? You could say that Herschel pioneered the field of carrying out large sky surveys, although the technology that he used was quite a bit different than we do today. But with his telescopes, at that time he was already able to see the myriad of stars that you could see here in M15. For example, in any modern moderately large amateur telescope, these are really very beautiful objects. So you can ask, after 250 years of studying these objects, what is there still to learn about them? And it turns out that there's quite a bit that we still don't understand about them. Okay, M15. I want to dwell a little bit on the terminology. Why do we actually use the word globular clusters? And so that also goes back to Herschel. And if you read Herschel's early papers, he doesn't actually talk about globular clusters, but he made this drawing of M53 that was also included in Messier's catalog, right? And he mentions that this cluster is one of the most beautiful objects that he has seen in the heavens, and he refers to it as a solid ball consisting of small stars. And then the year after, he already uses the word globular here, right? Speculating a little bit about how objects like that might form, that stars might condense towards the center and form themselves into a cluster of stars of almost a globular figure, more or less regularly so. And then finally in 1789, we see here the term globular clusters of stars mentioned, as far as I can trace it, for the first time. Now this is of course all based on morphology of these objects, how they look visually through a telescope. Today we know quite a bit more about them than that. One thing that we know about globular clusters is that they tend to be very old. As you can see here in this color magnitude diagram of 47 Tucanae, it's fit very well by basically a single isochrone there, with an age of, in this case, about 13 gigayears. And most of the scatter that you see here, or essentially basically all of the scatter around this isochrone, can be explained by observational errors. So we think of globular clusters as some of the best examples we have in nature of simple stellar populations. That means stellar populations with a single age and a single metallicity, although as we'll also see later in the talk, the picture is again quite a bit more complicated than that. Now, globular clusters are very nice tracers of galactic halos in the Milky Way. About 2/3 of the globular clusters that we know are associated with the halo, kinematically, chemically, and so on. And so that makes them very nice tracers also in external galaxies. If you want to study the metal poor components of elliptical galaxies, for example, globular clusters are very nice for that because there are just so many of them. So it's sort of leads to the question, is there something special about globular clusters? That they're so dense, most of them very old, and if you show an image of M15 here next to an open cluster there, like the Pleiades, there's a huge difference in age, in mass, density, and also other things like metallicities and spatial distributions. So Shapley certainly thought that there was a fundamental difference between these two main classes, the globular clusters and the open clusters, and I think we owe this distinction to Shapley largely, so, or maybe we can blame it on him based on sort of your feelings about this. But this modern view of globular clusters and open clusters as two distinct things, I think, can be traced back to Shapley. It's not really clear that Herschel actually intended to make that distinction himself. Now, I don't want to argue too much about how we define objects or how we classify them. More interesting is perhaps whether there's something physically special about the way that globular clusters formed, as opposed to how star formation takes place today. So you could imagine that since they're so old, their formation might have something to do with unique conditions that were present only in the early universe. Right, so Peoples and Dickey noted that the gene's mass shortly after recombination is similar to the characteristic mass of globular clusters today, so maybe that's interesting. You could imagine thermal instabilities in galaxy halos initially playing a role, or maybe dark matter mini halos that collide, all kinds of things that would have been much more dominant and important in the early universe than they are today. Or sort of the alternative view, the other view, would be that globular clusters are just an outcome of normal star formation processes as they take place in the universe today, albeit under more extreme conditions. Obviously globular clusters forming like this are relatively rare today. But so I guess the fundamental question in that sense is whether this is sort of two really distinct things or part of a continuum with things that sort of fall in between. And I just saw this picture here on Astronomy Picture of the Day a few days ago, right? It's an object, a star cluster obviously, but is it an open cluster or a globular cluster? Not so easy to tell maybe if you just would see a picture of it, but it's quite a bit younger than something we would normally call a globular cluster, and it's also relatively metal rich. So this would probably fall in the category of an open cluster, but sometimes the boundary can be a little bit fuzzy. This is not a new discussion by any means. So you can go back to 1959 in the Astronomical Journal. You will find this summary here of a discussion that took place at a AAS meeting that year in Toronto, where people discussed the differences among globular clusters, and there's a long discussion there going on about how you should classify them and what they have in common and not, and et cetera, et cetera. At some point, Morgan says, suppose we were making a new catalog of clusters, what should then be the natural division between open clusters and globular clusters, right? And they go back and forth and they talk about density and color magnitude diagram and metallicities, all those kind of things. And they always run into these intermediate cases. So Sandage answer is that, well, I really don't know, he says, we should just ask Ms. Hogg, she's the expert. She has the definitive lists, right? And then de Vaucouleurs chips in and says that we have a problem here that you also encounter in other branches of science, where it's often difficult to pin down the exact boundaries. And you have that in biology and zoology and et cetera, et cetera. So this was just based on things that were known in 1959. Since then, the situation has become even more complicated, if you like. Right, we have objects like this one, the antennae galaxies merging, and merger of two major spirals. And if you zoom in on the overlap region there, you see all these point sources there that are actually not quite point sources in an HST image. They are slightly extended. and they have sizes that are consistent with sizes of globular clusters. So half-light radii of a few parsecs, 3 to 4 parsecs or so. And from broadband photometry, you can also age date them. So this plot here now just shows those point sources or near point sources in the antennae with luminosity versus the age here determined from broadband colors. And you can see lines here that correspond to constant masses. So in the antennae, there are few clusters that fall above this 1 million solar mass line there. This we would call a globular cluster for sure if it were 13 billion years old, except that these go all the way down to stuff that is still forming today. Right? And there's a large number of clusters here, around 10 to the 5 solar masses, and more as you go further down. So that becomes then a little bit more difficult to say, are these the equivalents of globular clusters, but they certainly look like it. And just to make the point that you see objects like that not just in merging galaxies, this is another example in a spiral galaxy, a relatively normal spiral galaxy, although one that has a relatively high star formation rate intensity. And over here in the star forming complex, you can zoom in, and with HST you see again this very massive star cluster there with a mass of about 1 million solar masses. This is actually dynamically confirmed, so we have a measurement of the velocity dispersion of the stars in the cluster, which is about 10 kilometers per second. And so that's a dynamically confirmed mass of 1 million solar masses and an age of about 15 million years instead of 15 billion years, 10 billion, 13 billion years, whatever. So I would say, around this time, 2004, 2005 or so, I would have, stated quite strongly, these are just young globular clusters, right? There is not really that much doubt about that. If you let them evolve for Hubble time, they may lose some mass, and depending on their exact, history, whether they encounter a giant molecular cloud or something they might disrupt or not, but if you put them out in the halo and let them sit there by themselves and evolve in a Hubble time from now, you would see them as globular clusters. There are some differences between the young cluster populations and old globular cluster populations that one has to worry about maybe a little bit. One is the mass functions. So if you plot up the mass function of old globular clusters in the Milky Way or most other galaxies, you will find that it is roughly of this log normal shape, right? So if you plot absolute histogram of the absolute magnitudes, you will see that you get something that looks more or less like a Gaussian, right? So one histogram there is the Milky Way, that's the open one, and the blue one is the histogram for all the globular clusters around dwarf galaxies and the local group combined. So they don't look very different. There are some differences from galaxy to another, where exactly this peak is and how broad it is. But in the first approximation, it's quite remarkably universal and different from what we see in the young cluster systems. Right, so in the antennae and in many other young cluster populations, the mass function looks more like this. So it keeps rising down to low masses. So what is responsible for this difference? Well, the prevailing picture, I would say, is that this is probably due to cluster disruption. The low mass clusters are just easier to disrupt. They live shorter than the more massive ones. So over time, over Hubble time, you can probably erode away this low mass tail, right? And then you can end up with something that looks very much like the mass function that you see in the old globular cluster systems. This is painting with a very broad brush, right? This is not saying that all the details of this picture are completely understood. But I think that as of 10, 15, 20 years ago or so, there was somewhat more or less a consensus. This is probably the picture that we should have in mind, and certainly this is the picture that I had in mind at that time, and it was very much in line with this landmark paper here that came out by Elmegren and Efremov in the late 90s, where they proposed this universal formation mechanism for open clusters and globular clusters, and they say, well, all it really takes to form a massive globular cluster is a high interstellar medium gas density and pressure, so that you can assemble a sufficient amount of gas at a sufficient high density within a small volume, and then you should get a massive globular cluster out of that. And the mass spectrum that we see in these young cluster populations probably comes out of the mass spectrum that we see in the interstellar medium. Right? And then the fact that the old halo clusters are, that there are less, that there are fewer of the low mass old clusters, that is probably because of a Hubble time of cluster dissolution. Okay, now what sort of turned this picture a little bit upside down, at least in my mind, was then the issue here of multiple populations. So I remember very distinctly actually when I was at ESO, Gianpaolo Piotto gave a colloquium there back around 2003 or 2004, where he showed the color magnitude diagrams that they had obtained for Omega Centauri. This is a slightly more recent paper, but the story is the same, right? That you see the color magnitude diagram here with the main sequence and the giant branch there, the horizontal branch, but not one single isochrone can fit that. You have all these multiple subgiant branches and turn-offs there. And you can look at the main sequence here and see that it's not actually one main sequence. There are two parallel main sequences. Now, it was known already for quite some time that Omega Centauri has a metallicity spread that has been known since the 1970s. And you can see that the RGB here is quite broad. But the really big surprise came when metallicities were actually measured for the stars here on the different main sequences. So ordinarily, you would expect that metal-rich stars have a redder color, just because you have more line blanketing in the blue. So the metal-rich stars should fall over here, and the metal-poor stars should fall over there. And what we find from spectroscopic measurements is the exact opposite. So when you actually measure metallicities, you find that these stars are the metal-rich ones, these stars here are metal-poor ones, and the only way that you can really explain that is by also playing with the helium content. So if you increase the helium mass fraction to something like 40%, you can explain this. And then these blue stars would have this super high helium abundances, which just increase the mean molecular weight inside the stars, right, and make them more compact and more luminous. Okay, so that was Omega Centauri. Okay, then you can say Omega Centauri is maybe a bit of a peculiar object anyway, right, because it's the most massive globular cluster in the Milky Way, and maybe it's not really a globular cluster, maybe it's the remnant of an accreted dwarf or something like that. So if it was just Omega Cen, then maybe this would be sort of an interesting curiosity, but not something of greater relevance to globular clusters necessarily. But it is quite clear that Omega Centauri is not the only case. Here's another one, NGC 2808, again with multiple parallel main sequences here that you can see in HST photometry. And here it is clear that metallicity, an overall metallicity spread, doesn't really play any significant role, because NGC 2808, if you look at the heavy elements, there is essentially no spread. Right, so this is just a simple stellar population, apart from the fact that you see these multiple sequences here, that you again need then a helium spread to explain. So that's NGC 2808, the color magnitude diagram. There's also a measurement of chemical abundances of other elements on these different sequences. Right? And you see that the stars on the red sequence here, again, the ones that have a normal helium abundance, they also have normal halo-like chemical composition in other respects. But then if you look at the stars here on the blue sequence, the ones that have high helium abundance, they also have enhanced abundances of other elements like aluminium and sodium and nitrogen, and they're depleted in carbon and magnesium. But as I said, the blue and the red sequences, they have the same abundances of higher, more heavy elements, calcium, iron, and so on. So that is a big challenge, basically, when you talk about multiple populations, to explain and try to understand how do you get something like that. And so that's what I'm going to spend a little bit more time on. I just want to sort of wrap it up a little bit by saying that by now it's clear that essentially every globular cluster shows this. So it's not something that is seen in a small number of clusters. This is from the nice paper by Piotto et al. Again a couple of years ago, where you see now these color magnitude diagrams involving UV colors. So this C index is just a combination of color indices that involve ultraviolet filters on HST. And you see basically in all of them that there's a large spread here in the colors on the red giant branch and also on the main sequence. So this is quite universal. You see it everywhere. If you take the whole, so these are just the first 12 panels from their paper, right? I could have taken another 12 clusters, and it would have looked similar. But there's also some variety, right? We have NGC 2808, again here with 3 sequences in this particular color combination. If you add other colors, you may identify even more, 7, 8, 9 subpopulations with distinct chemical composition. In others, it's maybe a little bit more continuous, right? And in others, you see 2 distinct sequences very clearly. So that's also something we have to allow for this ubiquity, but at the same time, variety in the properties. Now, how could we have missed this for so long? So these color magnitude diagrams here are very spectacular, right, in showing the multiple sequences. And that really has to do with the particular choice of filters that you have to use in order to detect them. So as I said, these are UV filters, and you can understand that by looking at the spectra of these stars in the ultraviolet part of the spectrum. So here I've shown 2 model spectra for normal composition and for enriched composition. And you see these different molecular absorption bands marked here, right? CH, CN, NH, and OH. And it's clear that if you change the abundances of these light elements, carbon, nitrogen, and oxygen, and so on, then you're also going to change the strength of these molecular bands. And this then shows up in the broadband colors that you can form using these filter combinations here. You don't have those absorption bands further into the optical and red. So if you just make a B minus V or V minus I color magnitude diagram, for most globular clusters you're not really going to see anything, except for the ones that have these large helium abundance variations. But that's not all the clusters. It's just, in most clusters, the helium abundance variation is actually relatively minor. In that sense, omega Cen and 2808 are sort of a bit exceptional. That's the photometry. There's also spectroscopic evidence of multiple populations. This actually goes back long before the color magnitude diagrams were first published, right, going back to the 70s and 80s. People already knew that some of the light elements were behaving strangely in globular clusters, and this is from the large study by Carretta et al., where you see now for each panel here is one globular cluster, right, and you see measurements of sodium versus oxygen normalized to iron, and each cluster has this anti-correlation with some stars that have relatively normal, meaning supersolar oxygen to iron ratios, typical for halo stars, right? And relatively low sodium to iron ratios, right? And then there's these stars up here that are strongly enhanced in sodium and depleted in oxygen. So this is something you see very commonly in globular clusters. In fact, Carretta suggested this is how you should define a globular cluster. He said you should define a globular cluster as an object that shows the sodium-oxygen anti-correlation. So you can adopt that definition, of course, if you like. It is quite far from Herschel's original classification, obviously, but it's just a way of emphasizing how common this really is. Right, so just to summarize here, what are the key points about multiple populations in globular clusters? So they are seen everywhere, right? Certainly the sodium-oxygen and these nitrogen-carbon anti-correlation. That's practically every cluster that shows this. And some clusters show magnesium-aluminium anti-correlations as well, and a large helium spread. On top of that, they then show very little spread in heavier elements like calcium and iron, typically within the measurement errors, which are of this order of magnitude here, right? And then the anomalous fractions are very high. Typically more than half of the stars in a given cluster are affected, right? So the normal stars would live down here, right? But then, and this is where you would find stars, halo stars. If you just take a sample of stars in the halo, they're all going to be down here mostly. But then in globular clusters, you have all these stars falling up here. And so this is a challenge to explain how you get that. And so it's clear it cannot just be some normal chemical self-enrichment effect, right, having to do with supernovae or so, because if supernovae contributed to this, then you would also get a spread in elements like calcium and iron. So you have to think of other ways of doing this. And that has also been recognized for some time. What a likely or a possible way to do this might be, right? So having these light element abundance variations sort of hints at proton capture nucleosynthesis, hot hydrogen burning, where you can have these different chains here going on, right, where you can increase sodium, and you can reduce oxygen, and you can turn magnesium into aluminium, and so on. Yeah, so those are sort of the plausible nuclear reactions that are responsible for this. And then the question becomes, where can that happen? And the problem you then run into is that these reactions really require quite high temperatures. So you don't have to see this plot here, which is a little bit, shows up a little bit poorly. It's just supposed to illustrate that the reaction rates really take off once you reach temperatures above 20 million Kelvin or so. And you don't have those kind of temperatures in globular cluster stars today, especially the stars on the main sequence, right? They just, even in the core, they are not that hot. So they have to have formed like that. So they must have formed out of material that was somehow enriched with this polluted material. So how did it become polluted? Where did that polluted material come from that led to the formation of these enriched stars? And again, there are a couple of candidates that have been discussed in some detail in the literature. Of course, in more massive main sequence stars, you can get high temperatures like that. So if you have an O star like that, you can have it, have these reactions going on in the center of the star. And then the question just becomes, how do you then make that material, that processed material, available for star formation without requiring that you have to wait for the star to explode as a supernova? Right. So then what is proposed here in the scenario by Francis and Charbonnel and de Cresson and others is that if these stars are very fast rotating at near breakup speed, you can set up flows within the star that can mix material up to the surface and lose it so that it ends up in a disk here, a little bit like you have in BE stars. And then you can maybe somehow manage to form stars out of that disk material there, right? So that's one possible avenue. The massive stars there, fast rotating massive stars, or maybe binary stars could play a role as well. If you have two binary stars merging, maybe you could get the material dispersed out and form new stars out of it. And the other possibility is AGB stars, massive AGB stars with masses above 4 to 5 solar masses or so, that also get very hot at the bottom of the convective envelope there. So you can have the proton capture reactions going on down here, and then they get transported up to the surface of the star, and at the end you get a wind from these AGB stars, and you might then imagine that that material could somehow be used to form a second population of stars out of this enriched material. Those are the two main classes of polluters that people have discussed. So the picture that we then could have in mind of how a globular cluster would form in a sort of very cartoonish form here is that you have a star cluster here that has just been born by normal processes, whatever that is. Right, and then after a while you have these first generation polluters that start to get rid of some polluted material there, right? So either the AGB stars or the fast rotating massive stars. So there would be some delay from here to here, depending on which class of the polluters you prefer. And now, my nice animation there. So then this gas here has to become available for star formation. So maybe there's some sort of cooling flow setting in, and you have this material settling in the center, right? And you could form some new stars of it. And that's basically the picture. So then we run into a problem immediately, that is the so-called mass budget problem. Can you actually form enough polluted stars in this way? And you can do a very simple calculation here, right? Suppose you form a cluster with some initial mass, all first generation stars, and then you are able to produce some amount of polluted gas, say with an efficiency beta there, where that will typically be just a few percent, 5% or so for the massive AGB star scenario. So if you can form new stars out of that material with 100% efficiency, right, then it's very easy. That is the mass of your second generation, which is less than the mass of the initial generation. Of course, you're going to lose some mass due to stellar evolution over time. So if we suppose that this initial population here formed with a normal saltpeter or Kruper-like IMF, then you're going to lose about half of the mass just due to stellar evolution over a Hubble time. So after 12 gigayears, you have 50% of the initial mass of the first generation left. And if you suppose that the second generation stars had a bottom-heavy IMF, so that after a Hubble time you still have all of the stars left, right? Then this mass would still be the same as it was to begin with. But you have to make that assumption. And so then you can divide these two numbers by each other, right? And see that you end up with a fraction of something like 10 to 1, which is very far off the 1 to 1 fraction that we actually observe in globular clusters. Right? So that is the fundamental problem here with the mass budget. So what is then proposed is that, if the second generation, in this case we would be talking about distinct generations, right? But I sort of try to avoid this word of generations. But you would end up with these enriched stars in the middle here, right? And so maybe you could imagine that it would be easier to lose first generation, the normal stars from the outer parts of the cluster. So those sort of 9 out of 10 first generation stars fly away, leave the cluster, and in the middle you're left with an equal number of normal and enriched stars. So I think in practice, dynamically it's very hard to make this work. So there are some simulations that have been able to do this, but they require a very strong tidal field, and they require the second generation to start essentially right in the middle of the cluster, right? And if the tidal field then is so strong that you're able to strip away the outer parts before the cluster starts mixing dynamically, then this might perhaps just work under some circumstances, but as a general mechanism, I don't know. I think it is questionable whether this is going to work in praxis. But suppose it could. Okay, suppose it could work. Then all these stars should then be available. They should be present somewhere in the galactic halo, and then the Milky Way that might be possible. Today, about a couple of % of the mass of the Milky Way stellar halo is in the form of globular clusters. So that would say, maybe 20% of the Milky Way stellar halo would be, as a minimum, stars that have been lost from globular clusters. That might be doable, but there are other environments where this gets much harder. So one such place is the Fornax dwarf galaxy here, right? Fornax dwarf spheroidal, which has 5 globular clusters. That's a lot of clusters for such a small galaxy. In other words, it has a very high specific frequency. As a fraction of the total stellar mass in Fornax, the globular clusters actually constitute about the same fraction as in the galactic halo. But once you start to look at the metallicity distributions, things get a bit more interesting. So this is a plot that shows the metallicities of field stars in Fornax, together with the metallicities of the globular clusters. So you can see by eye here that those distributions are very different. And if you correct for spatial coverage and so on, you can bin that up as histograms, and you end up with a histogram that looks like this. So this is the metallicity distribution of the field stars. This is the distribution of the globular clusters. So there's a big difference there. And it turns out that down in this tail here, below -2 or so, there's just a few million solar masses of stars, 3 million solar masses or so. And there's about 1 million solar masses in globular clusters. So a quarter of the stars or so belong to globular clusters down there. And then it becomes difficult to explain what happened to all those stars that were supposedly lost from globular clusters if they should have been a factor of 10 more massive initially. Right? And this is before we start to consider any other mass loss mechanisms, right? Suppose these clusters formed out of a Schechter function where you had to erode away the low mass end of that. That would probably give you another factor of 10 as well, right? So then this becomes all very difficult. Is Fornax unique? Not really, it turns out. So we now have data for a few other galaxies in the local group where we have looked at the globular clusters, other people have looked at the field stars, and then we can compare. So that's Fornax. WLM is another dwarf galaxy. There's just one globular cluster, but again it constitutes a very large fraction of the field stars. IKN is another extreme one. NGC 147 a little bit less so, but you still see this offset between the field star and the globular cluster metallicity distribution. I just want to spend one slide here saying a little bit more about the detailed abundances of these clusters. Can we be sure that they actually have multiple populations? And we've been developing techniques to try to measure abundances of globular clusters from integrated light spectra. So on the left here you can see some observed integrated light spectra of these globular clusters in the dwarf galaxies. And the red curves here are our best fitting models around the sodium lines there, so the lines are not very strong and sort of difficult to measure, but we're able to pull out some sodium abundances nevertheless that look like this, right? So the colored dots are our measurements. So in all cases they have sodium abundances that are higher than what you see in Milky Way field stars, but similar to what you get if you calculate the average values for galactic globular clusters. So I think this is at least a quite strong hint that these clusters are probably not very different from their Milky Way counterparts in terms of hosting multiple populations. And in the case of Fornax, we actually have photometry of the stars as well, so it's a bit further away, right? So the measurements are more difficult. But again, when you use these UV colors here, you get a color spread that is much larger than what you can explain just from observational errors. So I think the Fornax globular clusters, again, host multiple populations just like the Milky Way globular clusters do. Good. So let me move on then to the last bit of the talk here and say a little bit about where do we actually find multiple populations, and more specifically, why in globular clusters, why not in open clusters, for example. And so the traditional thinking would be that this is probably related to the high masses of the globular clusters, right? So this is from a paper by Graton, where the red pentagons here are globular clusters that show the sodium-oxygen anticorrelation. The green crosses here are clusters that don't show the sodium-oxygen anticorrelation, that the other ones are just clusters that haven't been looked at, so we can't really tell one way or the other. But you can draw a line there and say somewhere around 10 to the 5 solar masses. It looks like there might be a cut, but of course you could also just draw a line like that and say maybe clusters that are younger than, whatever is 80% of the age of the clusters over here don't show it, and the old ones do show it. And the problem in making this distinction is that we have no clusters up here, right, and no clusters down here. These guys have probably disrupted, so they're hard to find, but we can hope to maybe try to fill in this region here by looking for massive clusters that have formed more recently and see if they have multiple populations. Right, so fill in this green area here, basically. What do these clusters do in terms of multiple populations? So in the Magellanic Clouds, there are some clusters that sort of start to approach this regime here. Younger clusters with masses just around 10 to the 5 solar masses. One of them is NGC 1806 that was looked at already by Alessio Mucciarelli a few years ago. Right, here's the color magnitude diagram where you see the RGB very narrow. You can actually distinguish the AGB from the RGB there, but each of them is really narrow even when you use this color combination here that involves UV colors. So there is no evidence from the CMD of an abundance spread there, and also from spectroscopy that Alessio did as well. These data points here are stars in NGC 1806, and there's just no evidence at all that there's any spread in sodium or oxygen abundance there. So we can at least put NGC 1806 on that plot and say this one should be a cross as well, right? But it would be maybe nice to have a few more to see what's going on. So that was the motivation behind a program that's been going on now for a bit with Bastion SPI, where we selected some more clusters in the LMC, basically the most massive ones that we could find, but spanning a range of ages. So those red circles here are the clusters that we have looked at. They're all above 10 to the 5 solar masses, but they have masses, at least present-day masses, in the same range as globular clusters that do show the sodium-oxygen anticorrelation. And we use a similar combination of filters, not exactly the same one as the Piotto study, but the idea is the same, right? That you can measure, in this case it's NH band here, that is sensitive to nitrogen abundance variations in these clusters. So as a test, we started with NGC 121, which is the only oldish globular cluster in the small Magellanic Cloud. And you see very nicely that you can separate out the two sequences there on the RGB. Right? So this was not a complete surprise. It's an old globular cluster. But it's actually still a little bit younger than most of the globular clusters in the Milky Way, right? Maybe 10.5 gigayears. So if you want to talk about formation redshift, that's going to be around 2 or so, right? So you're already sort of out of the regime where, you know, things like reionization or genes mass at recombination or so on start to become a little bit contrived. Anyway, but that's NGC 121. The next one was Lindsay 1, that is now 7.5 gigayears old, with a mass of 2 times 10 to the 5 solar masses, where you again see the split RGB here. You see it a little bit more clearly in the Hess diagram there. So that looks like there's a nitrogen spread there, and that is again confirmed by spectroscopy that was done by Katie Hollyhead, where you see again the red marker there is a nitrogen-rich star, and the blue ones are nitrogen-poor stars. So it's a relatively small overlapping sample there, but it definitely looks like Lindsay 1 also has multiple populations. This would now be a formation redshift of about 1. Right? Even younger, NGC 419 in the SMC, 1.5 gigayears, but still a relatively massive cluster there. Here's the image of the cluster, right? And this cluster shows this feature that we often see in intermediate age SMC and LMC clusters, this very extended main sequence turn-off region here that might be or might not be related to multiple populations. So the most sort of obvious interpretation would be that you see an age spread here. If it is indeed an age spread, it would be very large, a few 100 million years. There may be other explanations. Maybe it has something to do with stellar rotation, as Nate has proposed. But do we see evidence of abundant spreads? So you can look at the stars over here on the RGB. And let's see, there should be another figure coming here. Yeah, there it is. With the model lines for different composition. And again, here you see no evidence of multiple populations. You just see the stars with the solar scale composition. There are no nitrogen-rich stars there. So in spite of the extended main sequence turn-off here, NGC 419 doesn't seem to have any anomalies as far as chemical composition goes. So we can put another couple of objects over here, right? 419, 1806. And then these are the ones that do show the NGC 416 and the Lindsay 1 over there. There's still a bit of a gap here in the middle, so we would like to continue to decrease that gap. And so the last cluster that has been observed is NGC 1978, one of the most massive intermediate age clusters in the LMC, with an age of 1.9 gigayears, just slightly older than the 2 others that you saw before. And here you see, first of all, the extended main sequence turn-off has gone. It's very narrow here, the main sequence turn-off, and you can actually use that to constrain the age spread within the cluster, which turns out to be very small, basically unmeasurable within the errors, but no more, than 10 million years or so. Right? So that already makes it very difficult to use AGB stars as plausible polluters here to explain the multiple populations that we do see. So these are 2 different UV colors. I'm sorry, the label here is a bit hard to read, but this is 2 different color combinations that both use UV colors. You see that the stars that are red and blue in this color combination over here also tend to fall, on the right side and on the left side in this color combination over here. So this is just a test to see that there is actually a real detection of a spread there. So there is a nitrogen abundance spread in 1978, but no extended main sequence turn-off. So that is the youngest cluster that shows evidence of multiple populations, and I think this rules out quite strongly AGB stars as polluters here, at least for this particular cluster. Right, so we now have a red pentagon here, right, and we have some green crosses there. Again, it would be nice to have more clusters in between there. Unfortunately, you start to run out of LMC, SMC clusters, and going further away, it gets difficult to resolve the individual stars. But so you can say, okay, what happens there at this line here? Well, it's a main sequence turn-off of about 1.5 solar masses, what happens there. I'm not really sure if there's anything particularly special happening there. Below that star, that mass limit, stars tend to break magnetically, so that's maybe why the extended main sequence turn-off is gone in 1978, if it has something to do with stellar rotation. But what the connection is with the abundance spreads, I think is not at all clear. Then we have here the Madao plot, an old version of it, right? But just the cosmic star formation history as a function of redshift, with the Big Bang, over there, and today over here, and we can plot some clusters on it, right? NGC 121 in the SMC would have formed about here, right at the peak of the cosmic star formation rate plot there. Lindsay 1 over here, right? And NGC 419 over here, right? So I think it's very difficult to think of something related to cosmology that would be different between here and here, right? So maybe you have to look for some intrinsic explanation in the clusters having to do with whatever the stellar masses are at the turn-off or so. But honestly, I think there is no good explanation at the moment. So the summary, multiple populations, we have now found them in clusters that are as young as 2 gigayears. So this is not something that is really unique to old globular clusters, right? So going back to the question of classification, you could say that if a globular cluster is something that shows multiple populations, well, again, the ones that formed 10 or 13 billion years ago were not really special in that sense. And then we have to think of the explanation, right? We have to come up with a viable explanation that satisfies all these and many more observational constraints that are available, right? So that we have these spreads in the light element abundances, but not typically in the heavier elements. It's a large number of the stars that are affected. From dwarf galaxies, we have this constraint that the escape fractions from the globular clusters cannot have been as huge as seems to be required. There's a lot of diversity, and in some clusters, at least in NGC 1978 there, that looks like the age spread is very small. And then there's the question of the relation to the extended main sequence turn-offs that you see in some clusters. I don't know. Maybe one should consider other explanations than self-pollution. So I think ideas at this point are quite welcome. So maybe I'm just leaving you in a little bit of a state of confusion here, which is maybe appropriate because I think that is also the state of our understanding of these issues at the moment. And at the last slide, I will just go back to Herschel there, who stated, towards the end of his career, after having thought about globular clusters and other things for 30 or 40 years or so, that the globular clusters, as you can see, they are undoubtedly the most interesting objects in the heavens. So with that, I'm going to take questions. Thanks.
Thank you very much, Søren, for indeed both a fascinating and in the end, confusing talk about a great problem. Questions, please.
I have a question about if there's a pollution in binary stars. So if there would be one generation with an unequal mass binary, then the more massive one could transfer a small fraction of its mass to the smaller one and pollute it by a factor of 2 or something like that. To solve this mass budget problem. And then this binary is destroyed because the more massive one is exploding as a supernova. So is that a possible path?
So you mean that you would...
you need unequal mass binary, that the lower mass binary gets a high fraction of mass increase.
Yeah, but so I think you would still have to explain where that polluted material then comes from in the companion.
From the HME star, for example, or from rotating massive star. Just to solve this mass budget problem, that you...
Yeah, so I'm not sure if you could transfer enough mass. I guess you would still have the same problem, right? That if you have one star that, donates some amount of polluted material to a companion star, or whether that would end up working at the end, I'm not sure. I think there are ideas that have been proposed, that low mass binaries with some companion that is more massive might work. Whether there are enough binaries like that is perhaps a bit difficult.
So I had a question on the age differences of the different sequences. So for 1978, you said it was only a few million years. Is that typical, or do you usually don't see any age difference between the multiple sequences, or what do we actually know about the difference in age?
Yeah, so that's a good question. So 1978, I think, is the only case where we have a really good constraint and see multiple populations at the same time. In older globular clusters, it's much more difficult because you just lose the age resolution in a cluster that's 10 billion years old. An age difference of even 100 million years, that's just going to be 1%, right? And so that's sort of the kind of constraints that you can say in old globular clusters. The age spread can't be much larger than that because usually, they are very well fit by single isochrones. But it doesn't really rule out the AGB scenario, I would say. You could still allow that. There are some clusters where you see something that may look more like age spreads, like omega Cen, for example, where you have these parallel subgiant branches and multiple turn-offs. And there are a few other clusters where you see that. The problem there then becomes that if the sum of the light elements, carbon, nitrogen, and oxygen, changes, that could also produce similar morphology of the color magnitude diagrams. And that, I think, has not yet been ruled out, that for the small number of globular clusters, old globular clusters that do show parallel subgiant branches, that could be the explanation. If they really were age spreads, obviously those would be large age spreads.
I'll go to Freke first and then to you, Hans-Wout.
So I was a bit confused. So all these explanations, right, with a 25 solar mass rotating star or the AGB stars polluting it, like why does that only result in these crazy elemental abundances in globular clusters? Why does this same process not work in other regions of star formation?
So that's also a great point. I think the idea there is that a globular cluster, young globular cluster with a mass of 10 to the 6 solar masses or so, that would be a relatively deep potential well, right? And if you want to form new stars of this material, somehow you have to keep it in there, right? And so even an AGB star wind may have velocities of 10 or 15 kilometers per second or so. So in a typical open cluster, that would just disappear out of the cluster. So you wouldn't be able to keep it inside. You somehow need to keep it inside. And that's why this might then work in globular clusters that are more massive.
I had a related question. How much empirical evidence is there that such rapidly rotating stars or these massive AGB stars actually have those yields? Or is that purely something that comes out of calculation?
That is something which comes mostly out of calculations, and there are actually problems there as well. So most calculations don't give you the yields that you really need to explain this. So that's another problem. You have to tweak the AGV models quite a bit, for example, to get the right kind of abundance patterns. So that does not work automatically at all. If you just take any canonical AGV model, it's not going to give you the right abundances. But it's the best that we can come up with, right? Because you sort of think that this must have something to do with hydrogen burning, hot hydrogen burning. But the details, it's not clear that works.
Okay, in light of all these problems with the pollution scenarios, how much room do you think there is for stellar evolution actually to be the key for appearance of multiple populations?
Yes, I don't know. I mean, if there must be something fundamental that we don't understand about stellar evolution, right, in order to explain why you are able to have these abundance anti-correlations and also stars of very low mass, right? So I think that is one of the key constraints. In globular clusters, it's not just on the RGB, right? So you can say maybe there's something happening in RGB stars, but it's really also the main sequence stars. And people have done photometry in the infrared with wide field camera 3, where it goes, all the way down to as far as you can trace the main sequence, basically. So there should be something really fundamental that we're missing then in stellar evolution, maybe to do with binaries or so, I don't know.
Especially if you say like that, if we see multiple populations, if we look at stars that are less massive than 1.5 solar masses, and we generally don't see them in stars that are more massive than 1.5 solar masses.
Yes. Well, yes, but also, of course, I don't know. It's hard to say. I mean, so the stars above 1.5 solar masses, they start, I guess, to be hot enough that they could produce it in the cores. Also, you still have to get it up to the surface somehow. I think the more serious problem is with the low mass stars there, right? So of course, we don't really know what the low mass stars are doing in NGC 1978. So we have tried a few times to ask for time with HST to go really deep and probe down along the main sequence in NGC 1978, which would be a nice thing to do, but that has not been successful so far.
Are there any further questions for Søren? I had a question, but Nicola just asked it. So, I mean, I think it's quite. I mean, it would be a shock if it turns out that in the end, the answer is we don't understand stellar evolution, right? That beyond binaries. I mean, we always know we don't understand binaries.
But it has, I think, to make it work with binaries, it has to be a very special kind of binaries, right? And it is so universal, right? To find an explanation where binaries could somehow affect half of the low mass stars in a globular cluster, meaning that half of these low mass stars must have had a high mass companion. Maybe.
So one idea that has been around for a while and surfaces every now and then is stellar collisions. Because globular clusters are dense. So there was an Elmer Green paper earlier this year, but also Alice and Sills has worked on that. Do you have thoughts on that
collisions? Yes, I don't know. I haven't looked at that in detail.
Okay.
It's also an idea to explore, also in the context of collisions between massive stars, right? Maybe this is the one you were thinking about. That there is this idea that maybe it's not these fast rotating massive stars, or maybe it's not AGB stars. Maybe it's a supermassive stars. So if you would calculate a model for a 10,000 solar mass star or so, that actually gives you about the right yields. And the question is, can such stars form and exist? And maybe they could in a very dense star cluster if you have sort of a runaway collision process. So that has been discussed somewhat in the literature, not really developed in much detail yet. But considering where we are with the other ideas, I think it's also worth exploring for sure. Yeah.
Okay.